Hello, good afternoon, and welcome back. Okay, so today we will, to wrap up what's left in the dynamic programming chapter. So we're gonna finish the uh, matrix chain multiplication problem by looking at uh, two types of implementation, one bottom up and the other top down. And we'll go through some examples. And lastly, we're gonna uh, introduce another type of problems that can be solved by dynamic programming approaches, which is longest common sequence problem. So actually, we were here last time. We ended here. We looked at the code for solving a matrix chain um, multiplication problem by a bottom-up uh, manner. So let's do a few review here, a little bit review here. So so first of all, the bottom-up term, this terminology means that we solve the smallest subproblems first, and so later when we solve bigger problems, we can just look up the results to those smaller problems, right? So the code for the bottom-up implementation is here. And if we look at the outer for loop, there are three layers of for loop. If we look at this outer for loop, the loop counter is L. And this loop counter indicates or represents the size of the subproblem that we are solving. Okay, so we start from the smallest subproblem of size 2, okay, and we ended with size n, which is the original problem. Okay, and the second for loop, we have the uh, loop counter I. So I is actually the left end index of the sliding window of size L. So you can think of L, size L is kind of a sliding window. So L is first 2. So in the first iteration, we put a sliding window of size 2 from the beginning to the end of the sequence. Okay, so I, it always starts from 1 because it always starts from the leftmost side, and the ending point for I is n minus L plus 1. Okay, because it can, so when the right end of the sliding window reaches the end of the input sequence, then the left end index is n minus L plus 1. Okay, and the j is the index relative to I. Okay, so because j equals I plus L minus 1, so j minus I would be L minus 1, which means the length of the window is L. Okay, so this is also determined by I and L. Okay, so in this, within the body of the second for loop, we want to solve the subproblem that starts from index I and end with index J. Okay, so in order to solve that uh, specific subproblem, we need to look at how many ways to place the last layer of parentheses. So if, because this problem ranges from the left side is index I and the right side is index J, so there are k possible ways to place the last parenthesis, and k is from I to J minus 1. And the solution to this subproblem needs to be selected among these k possible ways of uh, the last layer of parentheses. Okay, so whenever we select a k, we will have two even smaller problems, which is from I to K and K plus 1 to J. And all these smaller subproblems will be looked up from this two-dimensional array, okay? And plus some additional cost of multiplying the two resulting matrices, okay? So the results to the subproblem from I to J will be stored in the ith row and the jth column in M, and the solution, the place to put the final layer of parentheses will be stored here in the S matrix. So this is a typical bottom-up implementation. So we can pay attention to several places here. So the Nij here is initialized to infinity because this is the problem we want to solve at the current iteration of the for loop. And then when solving this problem, we need to refer to even smaller subproblems. Okay, so these are the smaller subproblems, and these two smaller subproblems are solved in the previous iteration, or it is provided in the initialization step. Okay, so because in the first iteration of the for loop, L equals 2, and the subproblems will be of size 1. And all the size 1 subproblems are already initialized to 0 at the right beginning. So I think we're gonna go through one example for this bottom-up implementation. Okay, so let's say this is the matrices, the chain of matrices we want to compute the product. We want to conduct the chain multiplication. There are 4 matrices, and we know the dimensions are here. So the dimensions are stored in the array P. Okay, we call it P, and the index the index of P starts from 0. Okay, so P0 is 30, and 30 is the number of rows, which is the left component of the index of the dimension for matrix A1, and 35 is here is P1, right, and so on for A2, A3, and A4. Okay, so it's actually 5 distinct integer numbers stored in the P array. Okay, and then we initialize the matrix N and a matrix S. Okay, so you can see some additional values that are already put into the matrix. So this is the results after the first after the first iteration of the for loop is done. So initially, M and S should be empty, and according to the code, let me turn to the previous slide. Okay, according to the code, we will initialize M and S to be new tables, right? And then the line 3 to line 4 will initialize the indices that have the same row and the column index, which is the diagonal elements in M to be 0. So that's why in the next slide, we have the diagonal elements to be 0. Okay, so this turnaround, like the matrices has been turned around for 90 degrees. So this is not a typical way that we place matrices, because if you think of I to be the row index, which is from 1 to 4, right? And the J is the column index, it is 1 to 4 as well. So typically, when we write a matrix, it should be like this, right? It should be put in this horizontally aligned view. So it'll be easier to understand this is actually a matrix if we put it like this. So the rows are I, and the J's is the column, indicates the column. So first row, second row, third row, and fourth row, right? And the J is also from 1 to 2 to 3 to 4. Okay, so on on the left, in this left view, we actually only shows the half of the matrix because the other half is not necessary, because the J could never be uh, greater than so that the I could never be greater than J, because I is the left side of the sliding window and J is on the right side of the sliding window. So we actually uh, only takes the upper half of the matrix of the matrices. With, let me use another color. We only take the upper triangle area of the matrices, and including the diagonal elements. And we can also move the I to the right axis here. I is here, and I is 1, 2, 3, 4. Okay, and then we flip the triangle to left or counterclockwise by it's like not 90 degrees but 45 degrees. That will give us the current shape like this. Okay, so you can think of it a matrix, but only half of the matrix are useful, will be used in the computation. Okay, and S is smaller, and the index of J exclude 1. Okay, because you will see later why this is the case, because we don't need those redundant elements. And the 1, 2, 3 here actually are not there at the beginning. The whole matrices S is totally empty, and these 1, 2, 3 are the results after the first iteration of our computation. Okay, it's just shown here because I didn't add the animation code. Okay, so according to the algorithm, we need to solve the subproblem of size 2 first. And there are actually 3 of such size 2 subproblems. The first is to multiply A1 and A2, and the second is A2 times A3, and the third is A3 times A4. Okay, and according to the code, and we can also imagine this problem. The size 2 problem is just a regular matrix multiplication problem. There's no other ways to place the parentheses. We don't need to actually place our parentheses, right? It's just multiply A1 with A2. So the cost for multiply A1 and A2 can be directly obtained from the dimensions. We use the magic formula P times Q times R, right? So in this case, it is the dimension 30 times 35 times 15, which is the dimensions of A1 and A2. So we obtain this product, compute this product, and put it into the entry at matrix M at the first column, or at the first row and the second column, which indicates this is the solution for this particular type of for this specific subproblem. Okay, so we can put the number 15,750 into the entry here, right? Because this entry corresponds to the I1 and the J2. Okay, and also the S12 is 1. Okay, because this S indicates the last layer, the position of the last layer of parentheses, because this is just A1 times A2. So in theory, the position of the parentheses is after A1. So here we need to place A1 here. Okay. And for the second subproblem M23, it's basically the same thing, right? And for M34, we can compute it without similarly. Okay. So after all the size 2 subproblems are solved, we've got the final uh, uh, the the updated matrix M will be like this, right? With the three numbers filled in, and also the updated array S with this 1, 2, 3 filled in. Okay, so we can naturally know what the next step is. Now, after the subproblems of size 2 is solved, we need to solve the subproblems of size 3. Okay, so in matrix M, let's proceed on to the next slide. So next, we're gonna solve the subproblem of size 3. So we gotta fill out these matrix, these blanks, right? This entry has I equals 1 and j equals 3. So it is it indicates the problem of A1 times A2 times A3. Okay. And also this entry, it has I equals 2 and j equals 4, which means the subproblem of A2 times A3 times A4. Okay. So this round, we need to solve two subproblems of size 3. Okay, so to solve the first one, which is M13, to solve this one, there are two possible ways to place the k, right? We can let k to be 1, which is A1 times parentheses A2 times A3, right? So we can represent it by M11 plus M23. So M23 is the cost of solving the subproblem A2 times A3, which we already have. Okay, M23 is already here, okay, which is solved in the previous iteration. Okay, and also we need to plus P0 times P1 times P3, right? Because by following the principle of P times Q times R. So that's how we get the first candidate for this solution, which is 7,875. So the second possible way to place the K is to parentheses A1 and A2 first, okay? And then plus M33 alone, and plus P0 times P2 times P3. So this entry M12 is also computed in the previous step, okay? And all we need to do is to compare the magnitude, compare the two candidates. And of course, the first way is better. It has cost us less computation. So we will select this value for the problem of M13. Okay, and therefore the corresponding S matrix will also be updated with the value 1. Okay, because this is the place or the position of the last K parentheses. Okay, so the first value is 7,875, and similarly we solve the next subproblem of size 3, which is this entry, and we can obtain the solution to be 4,375. Oops. Okay, so we have this two new numbers, and also the two new numbers is placed to S. Okay, so we are building this pyramid, or this we are filling this matrices from bottom to in the bottom up way. We first fill up the lowest level and the one level above until we reach the top. So the top element here will contain the final solution that we want, right? So next, it's easy to infer that, okay, so now we need to solve the original problem, which is size 4. So for this problem, we are comparing three candidates, okay? The first one is to put the final parentheses around A2 and A4, okay, like this, final parenthesis like this. And the second candidate is to put one parenthesis around A1, A2, and A3 and A3 and A4. Okay? And the third candidate is from by wrapping up A1 and the A3 together. So anyway, we can find the smallest number among these three candidates and put these candidates into the top elements of the matrix M. And also the solution will be put into the matrix S. Okay. All right. So we've got the optimal solution. The total number of scalar multiplications to sum up the matrix chain from A1 to A4 is 9,375. Okay, and in order to obtain the specific solutions, like how at which position we need to place a parenthesis, we can just refer to the S matrix or S array. We call it a 2D array, but we use matrix to for a shorter name. So we look at this cell. So the S14 means S14 is 3, okay? So it means that the last layer should be around A1 and A3, right? And we use this S array to look at S13. So S13 is 1, as in this blue circle, which means that the best way to compute A1 times A2 times A3 is to parenthesis A2 and A3 together. Okay, and for A2 times A3, it directly tells us it's 2, which means there's no way to further split, right? So altogether, we should have by referring to the S matrix, it's easy to obtain the optimal way of parentheses. Okay. So we can define some procedures to print the solution, right? So it's kind of uses some tricks of recursive calls, like in this procedure, we use the S, which is already solved, and the starting index and endings of the subproblem. So whenever it's this just a one matrix, we will print the matrix. And in other case, we need to recursively call the function on the first half from I to index Sij and the right half. So these recursive calls will result in a path printed that will print the solution in the correct form. Okay. All right. So so far for the bottom-up solution of the dynamic for the matrix chain multiplication problem. So next we're going to look at a bit different solution, which is a top-down method, but the back-end data structure would be the same, and a bit different, a little bit difference is that this time we initialize the m with some special values indicates it has not yet been solved yet. So this is a quite similar method to the top-down solution for the rod cutting problem. If you recall, in rod cutting, we introduced the top-down first, and in the top-down method, we will need to initialize the arrays to infinity values. Okay, so whenever a subproblem from AI to AJ is encountered, we need to uh, compute its solution and store it in MIJ. Okay, and each time we encounter the same subproblem again, we just look it up and return that value in the array. And we follow the same principle in solving one subproblem here, and we need to look at k we need to look at a bunch of different candidates by iterate k from I to j. That's the same principle we use. Okay, so let's directly look at the. Oops, let me go to one more slide. Okay, so uh, we'll first we'll define two procedures. Okay, the first procedure is called memoized matrix chain. So this is the procedure that returns the solution. And this time we define M, right? And for we'll iterate over all the matrices in the table and initialize everything to be infinity. Okay? And we will call another lookup chain procedure, which we define in the next page by returning the solutions. So these M and P are the matrices and the dimensions, and the 1 and N is indicates the size the size of the original problem from 1 to N. So the key point is actually the lookup chain, uh, the helper function, the helper procedure. Okay. So in the lookup chain helper function, before we solve the subproblem, we'll look up the table to check whether it's solved or not. So if the entry is not infinity, then it means we have already solved it. So we don't need to solve it again. We just return the entry in that matrix. Okay. Okay, so that's the first if statement. In the next if statement, it is the simplest case of the subproblem. If it's the subproblem of size 1, then we just return 0. Okay, don't need to do any fancy computations. In other case, if the size of subproblem is greater than 1, then we should compare some candidates. Let k range iterates from I to j minus 1. Okay, and we use the principle, the optimal substructure principle to compute to find the optimal solution for the subproblem. Okay, we need to use a key q to store the results. So when we solve this subproblem, we will recursively call the function on the left subproblem from I to k, and the right subproblem from k plus 1 to j. Okay, still the same principle, plus some additional costs. And we will store that result if that q is has the smallest value. Okay, so q will be updated to the elements, will be stored to add to the matrix elements, matrix entry mij. Okay, because the mij is initially infinity. So in the first iteration of this for loop, the q, whatever q value is, it's always smaller than infinity. So the q will always be stored. So in the next iteration, if q is smaller, then the entry mij will be updated. Okay. And as a result, this entry will be returned to the previous function that called this lookup chain function. Okay? So that's for the top-down method. Okay, so it's basically follows the same principle, and we can summarize the difference between top-down versus bottom-up implementations. We can see a lot of common places between the rod cutting problem and this matrix chain multiplication problem, because both the top-down methods need to have recursive calls, okay, because it will use the recursive call to solve this to solve the subproblems, okay. And another common place is that at the beginning of the helper function, it always check whether one subproblem is solved or not. It will avoid solving the same problem repeatedly. Okay? And if we look at the bottom up method, we need to start with the smallest subproblem. Okay, and in those problems, we don't use recursive calls because we are sure that the we can directly use the lookup table, because we are sure that the lookup table already have some valid numbers, because we set up the loop in such a sequence that the shortest the smallest problem is solved before the larger ones are encountered. So that is the way we avoid conflict in the bottom up manner of implementation. Okay, so that's so far for the uh, matrix chain multiplication problem. We are done with both implementations. So next, we're gonna look at the last section of this dynamic programming chapter. We'll look at a very interesting problem called longest common subsequences. It's actually a very practical problem that is common in a lot of areas, including genetic engineering, biology, because when we want to compare the similarity between segments of genes, we're basically trying to find the longest common subsequences between two sequences. Okay, and in signal processing, in natural language processing, it's also has some applications. Okay? So the problem is that given two sequences of discrete, composed of discrete symbols, okay, so we have a vocabulary of discrete of limited size of limited number of symbols like A, B, C, D. Suppose that is the all the vocabulary we have. We only have A, B, C, D, four symbols. So the example, in this example, the X sequence is A, B, C, B, D, A, B, and Y is B, D, C, A, B, A. So we want to find the longest subsequence, and this subsequence does not have to be continuous. Okay, it can it can be like scattered into the sequence, like the BCA in X is here, BCA, okay, and it's also in Y, it's like BCA. So they exist in two sequences, but they are not necessarily they're not necessarily continuous. Okay, so in this case, BCA is a subsequence for both X and Y, but it is not the longest one. So we want to find the longest one. So in this case, BCBA is actually the longest one. Let me use another color to indicate it. So actually, BCBA B, A in X, and B, C, B, A. This subsequence is actually the longest among all longest subsequences. Okay, so here I use um, the word n, not the longest subsequence, because the longest common subsequence can have multiple instances. It is not it is not necessarily unique. Okay, there could be uh, multiple occurrences. So as I said, it can be used to measure the DNA's to similarity between the DNA sequences. Okay, so given this problem, um, it's probably not that straightforward to think of a dynamic programming from a dynamic programming perspective. Um, but we can, by looking at the condition that a common sequence, a common subsequence needs to satisfy, we are able to derive that this is actually a very classical application of dynamic programming thoughts. Okay. So let's formalize the problem a little bit more. Given two subsequences, x and y. So the length of x is lowercase m from 1 to n. And for y, the length is from the elements ranges from 1 to n, lowercase n. Okay, we wish to find the common subsequences that has the maximum length. So let's try to find if there's any optimal substructure or optimal structure in the problem, because that is the condition, one of the conditions a dynamic programming approach needs to satisfy. Okay, so if we want to find the longest, a longest common subsequence between x and y, we can look at two cases. We focus on the last elements, the ending elements, xm and ym. Okay, so if, because they are the ending matrix, which is or they are the ending elements, which is the rightmost elements. Okay, so if xm equals yn, if they are equal, then they must be included in the longest common subsequence, because they are the rightmost elements, right? Then the problem reduces to finding the longest subsequence problem, finding the longest common subsequence between the subsequence x1 to xm minus 1 and y1 to n minus 1, right? Because we know that xm and yn are for sure to be included in the into the longest common subsequence between x and y, and all we need to do is to find what is the LCS among the remainder parts to the left, right? So that is the first case. The two ending elements are equal, right? So we can indicate the subsequence in x that is 1 to the left of the ending elements to be x and x subscript n minus 1 to indicate as a notation. Okay, and we also denote the subsequence in y to be y subscript n minus 1. So we can write this problem, write this optimal substructure to be like this. The LCS between x and y is the LCS of the two subsequences plus 1, because this plus 1 means we are including the ending matrix because they are equal. Okay, so This is the first case of the optimal substructure, right? We can observe some recurrence, some recursive definitions, right? But of course, it's not going to be a recurrence. It's not going to be implemented by a pure recursive problem, because a recursive problem will solve the same problems repeatedly. And we definitely need to use dynamic programming. Okay, so the other case is a bit more complicated. So when the two ending matrices don't, when the two ending elements don't equal, they're not equal, okay? So then we basically want to compare two cases. The first case is the LCS between x, the original x, and y n minus 1, and the original y excluding the ending matrix. So this is the first case. And the second case is x n minus 1, the x removing the ending elements, and y, the original y. We are comparing these two candidates, and we want to choose the longer one, right? There should not be better solutions, right? We're just because the ending matrices, they are not equal, so we cannot include the ending matrix, the ending elements into the LCS solution. So we have to sacrifice either one, right? We should either sacrifice xm or yn, right? But we need to choose the better candidate by looking at which resulting LCS is longer. Okay, so that's why we need to use this expression, use the max element among the two, okay, to indicate this second case where the ending elements don't equal. So these two cases actually exhaustively listed all possible solutions to the all possible optimal substructures. So we basically should, based on this optimal substructure, to implement the dynamic programming approach. Okay, so we will use the same trick to rewrite the suboptimal structure with a tabular notation. Okay, so far the two equations on this slide, it's just a rewrite of the previous slide. Okay, and because we have this bizarre function named LCS there, and LCS is no more than a name, right? It can be any name. So it can also be a 2D array, right? So again, let's look at the parameters. The arguments is x and y, and x and y with subscripts. We should also simplify these notations, okay? Because the x without subscripts means we include all the n elements, and y without subscript means we include all the n matrices and all the n elements. So we can rewrite the two equations into a more compact form, a cleaner form, like we just remove the x and y's because they are not necessary. Okay, we use m and n as two integer numbers to indicate the inputs arguments, right? And it becomes n minus 1, n minus 1, right? So it's more, it looks more comfortable, right? We remove the x and y's because they are not necessary. And then we also simplify the LCS, right? Because the LCS of two integers is just indicates the entry of a 2D array, right? So why not we just use a 2D array C to store the results? Okay, so we can further simplify these two equations to this one. Okay, we just replace LCS with this lowercase c to indicate that this is a 2D array. Okay, so the 2D array C of ij is either this one if the two elements are equal in I and j, in x and y are equal, then it is this one. Otherwise, we need to choose between two cases if the two elements are not equal. Okay, so it's already a very simplified uh, notation for the suboptimal structure. So based on these simplified notation, we can implement the dynamic programming algorithm pretty easily. Okay, so we'll look at a bottom-up implementation here. Right, it takes into two parameters, which is x and y, right? And we record the length of x and the length of n. We initialize the parameters to be new arrays. Okay, we include the index. We let the index to start from 0 just for the convenience of computation. Okay, so it's a bottom-up implementation, which means we will set the for loops in a way that we start from the smallest subproblems. Okay, so I will iterate from 0 to n, j will from 0 to n. Okay, in the smallest case, when either I equals 0 or j equals 0, we will put zeros to these cells, to these entries. Okay, because whenever, well, if we are comparing two subsequence, if one sequence has 0 elements, then of course the common part is also 0. Okay, so in other cases, this else if and the else, these two actually summarize, implements the optimal substructure. Okay, so if the ending elements are equal, then the current entry should be this entry at location I minus 1 and j minus 1 plus 1. If the two elements are not equal, then we need to compare these two entries and choose the bigger one, right? And if we think of the meaning, the spatial meanings of these I minus 1 and the j minus 1, we can soon find that, okay, so in the 2D array, and the I is the row index, and what is I minus 1? It is the upper row, right? And j is the column index. So the meaning of j minus 1 is the column to the left, 1 to the left, right? So the elements at j of I minus 1 and j minus 1, so relatively to this array, we need to look at the upper left neighbor of that array, right? So this entry is actually the upper left neighbor of Cij. And in the second case, Cij minus 1 is the left neighbor because the column is 1 less. And the Ci minus 1j is the top neighbor, okay? So we are basically looking at the three neighbors of one particular entry, okay? Depending on whether the xi equals j. For example, in this case, y2 is c and x2 is also c. So they are equal. So we need to apply the code here. we will need to take the upper left neighbor here and +1, and we will compute this cell accordingly. Right? And this will be easy to, and the most important part is that the running time is quite simple. It's just the 2 layer of for loops, and which is basically um, bounded by the product of the length of the two input sequences. Okay. All right. So there will be two problems in the assignments for dynamic programming that ask you to fill up some blanks in the areas. The first one is about the matrix chain multiplication problem. The second one is about the LCS problem. So after this lecture, you should be able to do these problems. And lastly, let's do a brief review, recap. So dynamic programming is a very powerful algorithm. And in order to use it, we need to first observe the optimal substructure in the problem, which is to say the problem, the optimal solution to the problem should contain optimal solutions to the subproblems. Okay. And also, whenever, so the second condition is that there should be overlapping subproblems. Okay, so the subproblem space should be uh, uh, finite. It shouldn't be a like sorting problems, because the sorting problems, the subsequences, they never 100% overlap. Okay, and we need to check these two ingredients, like to check these two conditions to make sure that they are satisfied before we start thinking from a dynamic programming perspective. And that is all the content for the lecture today. And I have released assignments, 3 question sets for basically covering dynamic programming and the greedy algorithms that we're gonna cover in the next week. So you can start with the problems that you already know how to do first. Okay. Are there any questions? Okay, so if not, then thank you for coming. And
Professor, I have a question. In assignment 2, you have asked what will be the output. For some questions, it is like we have to compute the intermediate heaps.
yeah,
So
yeah,
you don't need the intermediate ones, just the initial one and the final one, right?
just the initial one and the final ones. Yes.
Okay, that's it.
Mhm. All right. Yeah, thank you, and enjoy the rest of the day. And let me know if you have concerns, issues. Let me know by emails. All right. Bye, bye, guys.